Good afternoon, everyone. This is Punith. So what I'm presenting now, the efforts that we have done in the material compatibility workstream. Myself and John Bean, we have been, and I think, running this for almost a year. Last year, we gave a brief update what we have done, but I think this is now has come a long way, involving participation from the chip manufacturers, server manufacturers, the tank designers, and then fluid manufacturers, all are coming together as an industry effort. And I would like to talk about what are the things that we have done in the last 1 year, involving all the community, and what the progress has been made, and where we are, and what is the next steps we have in plan. So I represent Shell, so I'm working as a technology manager, and John is actually the CTO for GRC, as we all know. So I think to give an overview of why we are driving this, I think OCP has a few principles that we need to align with each of these workstream efforts, which is running in parallel. So some of which would be efficiency, scale, openness, and impact. So we were asked to come up with explanation of the efforts that we do and how it fits well with the 4 baskets of principles that OCP is driving on. So it just tells you why immersion is important and how we play the role in this immersion space with material compatibility. What are the things that we need to keep in mind, and what are the things that has to be done to ensure that it is a success, and so that the industry is actually implementing this in large scale for deployments. So I think I was actually, when I was presenting a few weeks back to incubation committee, Jessica from Intel, actually, she gave a very good comment, is to create a problem statement, why this was driven for the last whole year, and why we believe that the efforts actually desired us to come up to the stage where we are today. So for me, especially in the immersion space, the one thing which was missing before, especially till, I would say, till last October, was that everybody was telling that they have the best fluids, but there was no standardization of how we analyze things for these fluids and how they were interacting with different components. So we actually collectively brainstormed ourselves with the committee, what are the things that we have gathered till now with experience, and how we can come to an open forum where we actually share, these are the things that probably without revealing their own IPs, but what is the industry wants to do, has to do, to ensure that it ends up as a success overall. So that's one point. Then the other point was that because there are so many fluids in the market, including single and two-phase, and then there are different components. So how do we come together and analyze where, with respect to, if I am actually, we are part of producing gas liquids, and there are players like polyalpha-olefin producers, there are two-phase producers. They would have done a lot of research for the last several years with various components, how we can come together and share their expertise that actually industry is requiring and looking for, so that we can actually put together in a big Excel sheet with respect to so many components, maybe 100 plus materials on a component level, and then all the set different type of fluids, which is single phase and two phase, and then share it to the industry so that if somebody is coming new, so that they have access to this document, go through this list. So this will be just a guidance document. It doesn't mean that, for example, if I choose one material works, that doesn't mean that it works for everyone. So this guidance will be taken forward to these OEMs where they actually use this as a reference, and then they will also do further investigation using this information. So, and then the big question was, what are the things that we need to measure properties-wise? So I think few had actually come up with the ideas that, okay, we need to do maybe 1, 2, and 3 types of properties, but others said we have a laundry list. So we had to come together not to make it more cumbersome, but more easy to the industry to practice this so that it can be implemented. And also, what was the selection criteria for those properties? So that is very, very important, because if you say one material is acceptable than the other, what is the metric is used to define this as acceptable or unacceptable, or maybe it is not usable for the application. So that was actually one of the key contributions that was made by the committee here. And then, what are the type of interactions between a fluid and a component? So I think there was a lot of discussions about whether it is a fluid to material interaction or it is actually something else is going on. So that we want to bring from the education standpoint as well as how we actually derive these understanding when actually they are doing the evaluation. So this was the criterias. I think I summarized it well. So we wanted to make sure that it creates a white paper which becomes a best practice for people to use so that they can implement. It involved, as mentioned earlier, several players, not just taking only one player in the ecosystem. So it involved fluid manufacturers, server, IT, OEMs. And then also end users were also contacted, because in the end, you might have a good document. We actually gave all the information, but end user also, their voice need to be heard. And we requested them to come in and chime in to say whether this is acceptable or there is something more need to be done. And also, I think the type of fluids that was used, and also how the behaviors were with respect to components have been actually evaluated. So there are a lot of people. So there is a big list. These are the people who have done the contribution for this white paper as well as for this work stream. There are a lot of other people who came in and gave sometimes, but these are actually the ones which actually helped drive from the beginning till the point where we are as we speak. So what does this encompass? So they have a broader matrix which involved ester manufacturers, which are basically synthetic-based and natural-based. Then we have GTL, gas to liquids, where Shell plays that role. And then we have synthetic hydrocarbons, which is typically the polyalpha olefins. So they also chimed in. And then the two types of categories of two-phase fluids that we considered in this conversation was basically the PFCs and PFPs. So those are the people. Basically, we set a target. So we have a laundry list of 120 components. And then each of these players, based on their database of the studies that were done, then they actually added the information to this matrix. So this doesn't mean the new players who are coming in with the newer products, they will be part of this conversation, because this work stream has just completed the task that was there for the last 1 year. But we will continue again starting from November, where we will bring in many more players, including more fluid suppliers. And then because there are a lot of people are changing components because the vendors have changed. So we want to bring those components into this massive list so that it is actually getting more information for people as we evolve in this industry. There are two links that has been shown here. This is basically, so I think Rolf was actually leading these efforts on the immersion requirements last year. And I think we published this document. Basically, this was about what are the immersion requirements. I think it involved so many aspects. One was on fluids as well. So this will be like a carry-on to that work stream, that efforts, the white paper that was published before, so that what else that we need to do when we're actually deep diving in the immersion space. And that's where our work stream was created, and we're actually carrying on. So this is a table, which is basically, it creates, irrespective of different players involved in fluid manufacturers, what are the key things that we require to make sure that, to begin with, for any immersion efforts. So you have to meet those criteria, the test properties listed against, and then we have requirements for fresh fluids, and then the requirements for materials which are there in the immersion tanks, considering the lifetime. Because if you just meet the fresh, but a lot of end users and even the practitioners involved, they would like to know how it behaves along the way. Let's say if we are claiming that the immersion will be probably filling a tank for 5 years, we don't expect to change fluid. During the 5th year or the 6th year or even the 10th year, how the fluid is behaving. That was one of the things that this experienced people who are involved in the immersion came in and basically suggested these are the good starting point. So this is where I would say the biggest improvement we are seeing now compared to this table is that Intel is now, I think it's already announced. So it's a white paper they are actually publishing. It is going through our work stream where I'm actually leading that efforts, wherein they are coming up with performance-based specifications. So this is basically a starting point, the specifications for the fluids, but now we are actually coming up with figure of merits. So with all the fluids, which is single phase, two phase, what are the key criteria that we need to have to ensure that those materials would perform to the real workloads and also with the real environments? Yeah, I think there are few properties, but all these fluids have to perform like a dielectric fluid. So if somebody is thinking this is just an oil, there are other things which have to keep in mind because it has to perform because there is electricity involved. We don't want short circuiting. And basically, this should perform like a dielectric fluid. So that is the first and the foremost requirement here, making sure that it is working like an insulating fluid. So this is basically the key requirements. And then the new add-on that we actually amended in this workstream was the auto ignition. So there is always, when you are actually certifying a tank involving fluid, there has been a lot of discussions about what is the fire point requirements, what is the auto ignition requirements from the certification standpoint. I think it is a valid discussions. So we amended from 250 to 300 in this work stream, basically. So as I said, I think there are there was no standardization. So everybody was doing a different way of evaluation with respect to material compatibility. So they used to take components, run at different temperatures, and then tell us how the behavior was. But we came to a common agreement that if you want to accelerate the aging effect for the fluid when it is actually inside a immersion tank, then what is the temperature that we need to choose? The biggest contribution there was a gamut of test temperatures people have tested, all the way from, let's say, room temperature all the way to 120 degrees C. But I think finally, knowing that the silicon has a glass transition temperatures or degradation temperatures, so we would want to keep that in mind and then define what is the fluid temperatures that actually, if you run at these temperatures, it actually showcases you maybe 5th year or 6th year down the line how the fluid will be behaving with respect to compatibility. So requirements was 80 degrees C test temperature, and then we have durations. So duration was set for 2 weeks. So this testing, standardization was test temperature and the duration of testing. And then what are the properties that actually need to be evaluated when you're doing the testing? And then how do we analyze these results, whether that is considered to be acceptable or not, which I'm coming in the next slides. So one caveat here is, this is actually for fluids which have very high initial boiling points, especially for single phase. Now, we know the industry is also using two-phase fluids. So if you set 80 degrees criteria, the boiling points for two-phase generally would be close to 45, 50 degrees C. In that environments, then we actually allowing them to run at those boiling temperatures and do the evaluation with respect to compatibility for aging. So the criteria that we came up was, okay, we have acceptability, unacceptability, and then you have case-by-case basis. So we defined how much percentage we consider to be allowable. If it is unacceptable, so what is the quantitative measurement there? So based on the long efforts involved in the work stream with the data that came up with their own experience along the way, they do believe that if it is greater than 20%, then it is something that we have to address this right away. Because we don't want to see that we don't do the testing, we just put it in a tank, run the measurements, and then finally 3 months or down the line or 6 years, there is actually popping out of some capacitors. So then it is easily to say it failed, but we are not addressing how to fix this in the beginning before we go into the tank. So those are the quantitative measures that were said, less than 10% before and after. I mean, like if you take a capacitor and you're doing the fluid aging test, before you have some metric, after doing the testing, if it is the results we are testing with respect to color, dielectric fluid, a breakdown voltage, any parameter we choose, we want to ensure that those parameters are actually within the 10% allowable limits. In that sense, then that means that whatever the capacitor was designed for this application, it is still working well enough with the fluid that we are choosing. There were so many testing component materials that were chosen. There is a laundry list here. Why? Because these are all part of the ecosystem that goes inside a tank. And I think the biggest key informations that we wanted to draw are when silicon is in actually exposure with temperature with the fluids, how it behaves. Plastics, rubber, these are the three probably the hot products that we wanted to test and make sure those informations were available. And in the below section is basically all the parameters that was actually evaluated. And then the mechanisms. So what are the types of mechanisms that we see in material compatibility, whether it is a direct interaction between a fluid and a material? What are the type of issues that we see? If you see there on the top, these are all for single phase. These are the common issues or the things that people observe. Dissolution, absorption, chemical interaction, and then aging, and then moisture intake for certain fluids. There is an intuition because of the free radicals available in their molecular structure. There is always a tendency to absorb moisture when it is actually having open tank systems, for example. And basically, and the indirect interactions would be is mainly that is the dissolution and the aging. So this is one of the very big topic that is actually we are publishing here in this white paper is the level of expertise that is available in the market, understanding about two-phase fluids. So we knew that first table that I showed with 80 degrees C as the benchmarking, but then what else the two-phase fluid need to be actually looked into because they actually perform or they are actually their design of the fluid is quite different than single phase. So we actually address this issue with a methodology on soxalate extraction. So this is a method wherein this is actually soxalate arrangement where you have on the bottom, there is a round flask that's where you fill in the fluid. And then the black object you're seeing, basically that consider this as a component. And when you're actually boiling the fluid, then it goes into soxalate and then we are allowing it to do the reaction. This cycle keeps repeating as how long you want to run the test. Typically, this is run at the boiling points and for 2 weeks. And then you understand before and after whether the component had a reaction or not. The key ones here for two-phase would be is extraction and absorption. Those are the typical common issues that needs to be addressed when we're actually using the two-phase fluids. There will be, I think, some of the current practices would be is that if there are inert hydrocarbons that is not extracted, then if it remains in the fluid, so that should not hamper the thermal cooling performance because the way the mechanism with the two-phase is that it changes from liquid to vapor and condenses and back in as a fluid. And if they create a layer of inert hydrocarbons that will not allow to do the transition, the measure that they're actually recommending with the tank OEMs is to try to do the filtration with carbon activated material so that you remove this from the system so that you actually expect the behavior of the transitions between phase changes that will be allowed so that it helps in the heat extraction from the two-phase fluids. Yep, this is my last slide. Basically, I just took a snapshot. So if you see here, I'm just showing you, there is a laundry list, more than 120 components. The top left is the different types of rubber materials. It's actually part of the seals and the rubber in the market. There are different vendors. They manufacture differently. So this is just a template for you. For example, in this case, the ethylene propylene diene monomer, which is a typical EPDM material which is found, especially in the capacitors, when they're actually being exposed to these fluids at certain temperatures, they do have the behavior of showing high swelling. And when it shows you greater than 20%, then we consider this as like acceptable or not. Yeah, so I think that's, and also I think we would really expect that we want more participation here because there are much more things to be done. This is just a beginning because we have just done at the component level, but at the system level and the server level, compatibility is probably that's what I will be driving along with Kai, who is actually the new project lead in our work stream, so that we are now moving from the first phase to the second phase, and probably we also bring in with the third phase as well. Yeah, I would like to thank all the work stream efforts that was done by the entire team, because without them, this won't be possible, and I would like to thank each and every one. That's it. Thank you.